Welcome to qnawire.
Okay, so here you have one mass moving to the left, let's say, and then another mass that's moving in the opposite direction. And you're told, so let's call this mass B, let's call this mass G, because one is blue, one is green, and you are given some sets of information that you can essentially make use of here. So the first thing is that they tell you that the blue mass is 20% larger than the green mass. So we already know that the mass of the blue compared to the mass of the green will give you 1.2. So this is because if this is 20% larger, it means it's essentially the mass of the green plus 0.2 mass of the green, which will give you 1.2 mass of the green. So the ratio in their masses is going to be this right here. And they tell you that half the kinetic energy that you had before is converted to internal energy. So we're not worried about the half that's converted to internal energy. We're just going to worry about the half that stays kinetic energy. So you know now that Ki is equal to 2 Kf. Because if you keep half the kinetic energy to get the initial, just multiply by 2. So that's the second bit of information you have. Third bit is that again, actually this VGI is 10 meters per second. So that's the third bit of information that you have. And then the other thing they tell you is that their momenta are equal in magnitude but opposite direction. So you can actually immediately start by looking at that fact. So we know that Pi always has to be equal to Pf. We're always going to use that, so we can just write it here. But in this case, Pi, you're told, since these momenta are the same, but in opposite directions, what that tells you is that Pi, which is mBVBi plus mGVGi, since these two are the same in magnitude, but you know that the velocity of g is in the opposite direction, which means this value here is actually a negative, which would make that negative. So if you add these two equal values, you should get 0. So this means that Pi is actually 0, which means that Pf should also be 0. So already now you can see where this is going. So mBVBF plus mGVGF is actually also equal to 0. So this is just moving that down here. So this can be your equation 1 essentially to keep that. So we have two unknowns here. So clearly we need two equations for the velocities in order to find these two unknowns. So the next step is to now account for the kinetic energy of the system. So we can further simplify this if we want, because we know what the ratio of the masses is. So we know this is mb, this is mg, that's 0 over there. So anyway, so if we divide throughout by mg, what we get is that 1.2 VBF minus, or you can just keep it as a plus in this case because we don't know what direction it's going to go. This is going to be VGF, and that's equal to 0. So this, I have used that fact now here to simplify that equation. So this is just the same. So you can't now go back and plug it in here because it's the same equation. I just simplified a little bit. So now let's look at the kinetic energy. So you know that this is going to be the governing rule for the energies. So essentially, you can now calculate Ki. And Ki is just half, again, all the all the initial velocities squared, VGI, and this should be equal to twice. So 2kF is going to be equal to Ki. So which means the final kinetic energy is just half of this. So we can just go ahead and say that if you have this, you get the final. But in this case, we can, let's just simplify a little bit more here. So that's VBI squared plus MGVGI squared. So now KF is now going to be, again, half MB VBF squared plus M. And you know that that's just half the initial energy according to this equation here. So this is going to be half of this. So notice if you take half of this, you actually get a quarter of that. So this is going to be 1/4 MB VB squared, but this is VBI plus MG VGI squared. So this essentially is equation 2. But you're going to need to simplify it further, again, because you know the relationship between the masses, which is up here. So you can go ahead and remove these masses. So to simplify this, what I'm going to do is divide every term by mg. So if I divide this by mg here, I'm going to have the factor of 1.2 because mb over mg is 1.2. So that already makes that a little better to look at. Plus, this is mg over mg, which is 1. So that's just half VGF squared. And this, again, is mb. So mb over mg is 1.2. So that's just going to be 1.4, 1.2 VBI squared plus, this is just 1 VGI squared. So this is now slightly simpler. You can go ahead and remove the fractions if you want. That will help you in simplifying this as well, if you want to go ahead and remove all these fractionals over here. So now that you have a nice form here, now you can refer back to equation 1. Notice that equation 1 just gives you an expression that only has the velocities. So you can now choose which one you want to solve for first. So I choose to write my VGF in terms of VBF. So I know if I move this to the opposite side, I know that negative VGF is actually going to be equal to 1.2 VBF. So notice that, again, they're in opposite directions because their signs are different. So anywhere I see a VGF in this equation, I can plug in 1.2 VBF to simplify it. So there's a VGF here that's squared. So I'm going to put all of this in here and square it. And then let's see what it comes down to. So if once you put all of this in here, you find that this whole side here is going to have something that looks like this: 1.2 VBF squared plus half of 1.2 squared VBF squared. Because essentially we just put in this whole expression in here and squared it, and that's what we get. And so now we can go back to one of our equations here. So we know that the momenta were the same, but they were in opposite directions. The initial momenta were the same. So we can now also write another equation to simplify this. So if the momenta were the same before the collision, we know if they were the same in the opposite direction, we can actually just write it as mv v b I was equal to mg v g I, because the momenta were the same but in opposite directions. So this equation would directly lead you to something like this, but we're just comparing the magnitudes in this case. So notice I haven't taken into account the negative sign here because I know they're equal and opposite already. So I can just use this expression here. So I know the ratio of the masses, so I'm just going to go ahead and divide by mg on both sides. So that means that 1.2 VBI is actually equal to VGI in this case. So this will give you another equation again that you can use to simplify this, because you know VGI is 10. So if you plug in 10 here, you divide that by 1.2, you realize that VBI is actually equal to something around 8.333 going on here. So now you have VBI, you have VGI, and now you go back to this equation where you have VBF only, and now you have all these terms here. So this is the 8.333 and this is the 10. So that's 1.2, that whole expression squared plus 10 squared. So what you notice is that actually this whole expression here just comes down to something around 91 point. So I think this is 91.6 going forward here. And then once you simplify this left hand side here, you find that it's equal to 2.64 VBF squared. And then if you divide now by 2.64 and then take the square root of that whole thing, you find that your VBF is going to be the square root of that whole thing here, and that should give you something around 5.89 meters per second. That's VBF. And once you have VBF, you can now go all the way back to that equation to find VGF. So just multiply this by 1.2 and you get that VGF is actually equal to 7.07 meters per second.